Hello, and a very warm welcome to everyone. This is Utkarsh, and today I'll be talking about metamaterials and its boundless curious aspects in future days. Talking about the abstract in a very trivial sense, this presentation is a tribute designed to praise two great scientists who have set the world alight by stimulating boundless curiosity about metamaterials. To achieve this outcome, some simple discussions of refractive index are used as means of getting to the now famous concept of negative index. It presents some impressions of their backgrounds, including the fact that John Pendry is now known as Sir John Pendry. It is acknowledged that Victor Veselago truly guided the world along the track of negative refraction with a remarkable display of pre-science. It is asserted that metamaterials have a brilliant future, and that very important work is progressing towards the production of loss-free and active negative index and other forms of metamaterials. It pointed out that the control of light paths through the distortion of space is currently a major outcome from the groundbreaking work of the pioneers, and that, in fact, light concentrators and optical black holes may well be life-transforming consequences. Indeed, the whole world is indebted to John Pendry and Victor Veselago. Throughout this whole presentation, my focus encircles around a particular seeming impossible regime of the concept called invisibility. Invisibility cloak has long been one of the marvels of science fiction and fantasy. For example, Harry Potter. But the problem is that they usually violate the laws of optics and do not conform to any of the known properties of matter. Invisibility is a property that arises at atomic level. Maxwell equations and hence would be exceedingly difficult, if not possible, to duplicate using ordinary means. To make Harry Potter invisible, one would have to liquefy him, boil him to create steam, crystallize him, heat him again, and then cool him, all of which would be quite difficult to accomplish, even for a wizard. But perhaps the most promising new development involving invisibility is called metamaterials. They simply violate the laws of optics. This word is a combination of meta and material. Meta is a Greek word which means something beyond, altered, changed, or something advanced as presented. Metamaterials were first theorized in a paper by Soviet physicist Victor Veselago in 1967 and were shown to have weird optical properties such as negative refractive index and reverse Doppler effect. In 2006, researchers at Duke University in Durham, North Carolina and Imperial College in London successfully defied conventional wisdom and used metamaterials to make an object invisible to microwave radiation. Although there are still many hurdles to overcome, for the first time in history, we now have a blueprint to render an ordinary objects visible. So what are these metamaterials? They are substances that have optical properties not found in nature. Metamaterials are created by embedding tiny implants within substance that force electromagnetic waves to bend in unorthodox ways. At Duke University, scientists embedded tiny electrical circuits within copper bands that are arranged in flat, concentric circles. The result was a sophisticated mixture of ceramic, Teflon, fiber composites, and metal components. These tiny implants in the copper make it possible to bend and channel the path of microwave radiation in a specific way. Metamaterials can continuously alter and bend the path of microwaves so that they flow around a cylinder. For example, essentially making everything inside the cylinder invisible to microwaves. If the metamaterial can eliminate all reflection and shadows, then it can render an object totally invisible to that form of radiation. At the heart of metamaterials, there is an ability to manipulate something called index of refraction. Refraction is a bending of light as it moves through transparent media. If you put your hand in water or look through the lens of your glasses, you notice that water and glass distort and bend the path of the ordinary light. The reason that light bends in the glass and water is that light slows down when it enters a dense, transparent medium. The speed of light in pure vacuum is always remains the same. Light traveling through glass or water must pass through trillions of atoms and hence slows down. For example, the index of refraction is 1 for a vacuum, 1.0003 for air, 1.5 for glass, and 2.4 for diamond. Usually the denser the medium, the greater the degree of bending, and greater the index of refraction. Usually, the index of refraction is constant. A narrow beam of light is bent when it enters a glass and then keeps going in a straight line, but assume for the moment that you could control the index of refraction at will, so that it would change continuously at every point in the glass. As light moved in this new material, light could bend and meander in new directions, creating a path that would wander throughout the substance like a snake. If one could control the index of refraction inside the metamaterial so that the light passed around an object, then the object would become invisible. To do this metamaterial must have a negative index of refraction, which every optics textbook says is impossible. So the race is on for the visible light. Ever since the announcement that metamaterials have been fabricated in the laboratory, there has been a stampede of activity in this area, with new insights and startling breakthroughs coming every few months. The goal is very clear: to use nanotechnology to create metamaterials that can bend visible light, not just microwaves. A milestone in the quest for invisibility came when the silicon wafer etching technology was used by a group of scientists to create the first metamaterial that operates in the visible range of light. Scientists in Germany and at the US Department of Energy announced in early 2007 that, for the first time in history, they had fabricated a metamaterial that worked for red light. The impossible had been achieved in a remarkably short time. Physicist Kostas Tsoukalos of the MS laboratory in Iowa, with Stephen Leyden, Martin Wegner, and Gunnar Dolling of the University of Karlsruhe, Germany, were able to create metamaterial that had an index of -0.6 for the red light at the wavelength of 780 nanometer. The scientists first started with glass sheet and then deposited a thin coating of silver, magnesium, fluoride, and then another layer of silver, forming a sandwich of fluoride that was only 100 nanometer thick. Then, using standard etching techniques, they created a large array of microscopic square holes in the sandwich, creating a grid pattern resembling a fishnet. Then they passed a red light beam through the material and measured the index. It was -0.6. So what will be the future of metamaterials? Progress in metamaterials will accelerate in the future for the simple reason that there is already intense interest in creating transistors that use light beams rather than electricity. Already hundreds of millions of dollars are being invested in creating replacements for silicon technology, and research in metamaterials will benefit from these research efforts. With breakthroughs occurring in this field every few months, it's not surprising that some physicists see some sort of practical invisibility shield emerging out of the laboratory, perhaps within a few decades. In the next few years, for example, scientists are confident that they will be able to create metamaterials that can render an object totally invisible for one frequency of visible light, at least in 2 dimensions. Next, scientists will have to create metamaterials that can bend light in 3 dimensions also, not just for flat 2-dimensional surfaces. Photolithography has been perfected for making flat silicon wafers, but creating 3-dimensional metamaterials. will require stacking wafers in a complex fashion. After that, scientists will have to solve the problem of creating metamaterials that can bend not just one frequency but many. This will be perhaps the most difficult task, since the tiny implants that have been devised so far bend light of only one precise frequency. Scientists may have to create metamaterials based on layers, with each layer bending a specific frequency. Solution to this problem is not clear. As daunting as these difficulties are, scientists and engineers are optimistic that an invisibility shield of some sort can be built in the upcoming decades. I hope that I was able to convey my message through this presentation thoroughly. If you guys have any query or questions, please feel free to ask me at the comment section below and give a thumbs up. I would especially like to thank my professor and my friends for the support they have shown to me. Alright guys, so this is Utkarsh and see you next time.